2.5 Exponential Decay. Southwestern College, Professor Maria Olivas. Exponential decay. Objectives: solve applications involving exponential decay, including present value. 1. Exponential decay. Recall that functions of the form y equals ce raised to the kx power, where k is less than 0, represents exponential decay. I have drawn a cloud around the words exponential decay. I have boxed in the equation y equals ce raised to the kx power, where k is less than 0. This can also be written as y equals ce raised to the negative kx power, where k is greater than 0. And I have also boxed in the equation y equals ce raised to the negative kx power, where k is greater than 0. We have a graph that appears in quadrant 2 and quadrant 1, and it is decreasing from quadrant 2 to quadrant 1. Next to this graph, I'm going to write the limit as x approaches infinity of the function ce raised to the negative kx power equals 0. And if we look at this graph, we can see that as x is approaching infinity, this function is approaching 0. As with exponential growth, the derivative function is dy dx equals c times e raised to the negative kx power times negative k, which can then be written as dy dx equals negative ky. If you recall, y is equal to ce raised to the negative kx power. Since y is equal to ce raised to the negative kx power, I can replace the ce raised to the negative kx power with a y. I have highlighted the y. I have highlighted the ce raised to the negative kx power. Example 1. A radioactive element has a decay rate of 6.5% per day. That means the rate of change of the amount of the element A with respect to time, t, in days, can be represented by, we're going to go ahead and write down this derivative function as dA dt equals negative 0.065 times A. If we convert our 6.5% to decimal form, and we include that negative since it did say it was a decay rate, we could write that as dA dt equals negative 0.065 times A. Here, the negative 0.065 represents our negative k from the equation we had previously written up above. I'm going to highlight that in green, the negative k, and I'm going to highlight the negative 0.065 in green as well. And the a is going to be highlighted in yellow, as well as the y, which was already highlighted in yellow, so that you can see and make the comparison here of the parts that are in common with the equation. A. Let a sub 0 represent the initial amount of the element. Write the exponential function that models the situation. First thing I'm going to write is I'm going to write the equation y equals ce raised to the negative kx power. Underneath that equation, I'm going to write a of t equals a sub 0. I'm going to highlight the c in blue, and I'm also going to highlight the a sub 0 in blue, because these are the factors that correspond to each other. And then I'm going to multiply the a sub 0 by e raised to the negative 0.065 times t power. And I'm going to box in the equation of a of t. This represents our exponential function. B. Suppose initially there are 10 grams of the element. How much of the element will be left after 6 days? I'm going to double underline the word initially, and I'm going to underline the words there are 10 grams. From the word initially, I'm going to draw an arrow pointing upwards to the a sub 0, because whenever they use the word initially or initial value, I'm going to know that that's going to represent my a sub 0, my initial value. So underneath, I'm going to write a sub 0 equals 10, and then I'm going to write my equation a of t equals a sub 0 times e raised to the negative 0.065 times t power. I'm going to substitute for a sub 0. I'm going to substitute that with a 10. So a of t equals 10 times e raised to the negative 0.065 times t power. In the problem, it said how much of the element will be left after 6 days. So I'm going to substitute t with 6. A of 6 equals 10 times e raised to the negative 0.065 times 6 power. This is going to be approximately equal to 6.77 grams. And I'm going to box that answer in. C. After how long will exactly half of the original amount remain? This is called the half-life. I'm going to highlight the word half, and I'm going to highlight the words, this is called the half-life. I'm going to write down the equation a of t equals 10 times e raised to the negative 0.065 times t power. I'm going to highlight in blue the 10 that represents our initial value. And towards the right of this equation, I'm going to write down initial amount is equal to a sub 0, which is equal to 10 grams. We need to ask ourselves, how much is half of 10 grams? In order to find half of 10 grams, I'm going to divide 10 by 2. 10 divided by 2 is going to be equal to 5 grams. So we want to find how long it will be until exactly 5 grams are left of the original amount. I'm going to highlight the a of t in green, and I'm going to draw a green cloud around it and draw an arrow pointing downward. I'm going to draw a cloud around the 5 grams and draw an arrow pointing towards the a of t. I'm going to replace a of t with 5. So now our equation is going to be 5 equals 10 times e raised to the negative 0.065 times t power. In order to solve for t, I'm going to divide both sides of my equation by 10. On the right-hand side, tens will divide out. On the left-hand side, 5/10 will reduce to 1/2. Now I'm going to take the natural log of both sides. So now my equation is going to say 1/2 equals e raised to the negative 0.065 times t power. Now I'm going to take the natural log of both sides of the equation. So now we will have the natural log of 1/2 equals the natural log of e raised to the negative 0.065 t power. I'm going to draw star, and next to that, I'm going to write down that the natural log of 1/2 equals the natural log of 2 raised to the negative 1 power, which is equal to the negative natural log of 2. So if you recall, based off of our power property of logarithms, we can rewrite the natural log of 1/2 as negative natural log of 2, if we would like to do that. I'm going to draw an arrow from my equation that I had written previously, with an arrow pointing slightly upwards and towards the right. I'm going to write down the natural log of 1/2 equals negative 0.065 t times the natural log of e. I'm applying the power property of logarithms here. And then I'm going to write down the natural log of 1/2 equals negative 0.065 t times 1. And then the natural log of 1/2 equals negative 0.065 t. I'm going to lasso all the work that I've done up to this point for this problem C. I'm going to shrink it, and I'm going to move it slightly to the left so that I have more space to write. If I want to solve for t in this equation, I'm going to divide both sides here by negative 0.065. On the right-hand side, the negative 0.065s will divide out and just give me 1t. I'm going to highlight the natural log of 1/2 and the negative natural log of 2. I'm going to replace that natural log of 1/2 with the negative natural log of 2. So I'm going to write down t equals negative natural log of 2 over negative 0.065. So t is going to be equal to the natural log of 2 divided by 0.065. And now I'm going to label the units. This is referring to the number of days, so we're going to write that t is equal to the natural log of 2 divided by 0.065 days. If I would like to get an approximation for this, then this is going to be t is approximately equal to 10.66 days. I'm going to go ahead and I'm going to box in my answer that says t equals the natural log of 2 divided by 0.065 days. I'm going to go ahead and draw a red cloud around the place where I drew the star and I wrote the natural log of 1/2 equals the natural log of 2 raised to the negative 1 power, which equals negative natural log of 2. And I'm going to draw an arrow pointing downward to where I had written natural log of 1/2 divided by negative 0.065. So you can see exactly where I replaced the natural log of 1/2 with the negative natural log of 2. D. The element is considered safe when less than 1 gram remains. How many days will it take for the element to be considered safe? I have underlined the words less than 1 gram remains because this is what we're looking for. I'm going to go ahead and replace 1 where a of t would have gone in our equation. So our equation is going to be 1 equals 10 times e raised to the negative 0.065 t power. In order to solve for t, I'm going to go ahead and I'm going to divide by 10 to both sides of my equation. So I'm going to have 1 divided by 10 equals 10 times e raised to the negative 0.065 t divided by 10. The 10s will divide out on the right-hand side, and I'll be left with 1/10 equals e raised to the negative 0.065 t power. I'm going to take the natural log of both sides, so I'll have the natural log of 1/10 equals natural log of e raised to the negative 0.065 t power. Now I'll have the natural log of 0.1, or 1/10, is equal to negative 0.065 t times, and I'm just going to go ahead and write the natural log of e. So the natural log of 1/10 equals negative 0.065 t times 1, because the natural log of e is just equal to 1. I'm going to draw an arrow from this equation pointing upwards and towards the right to write my new equation here. I'm just going to go ahead and write the natural log of 1/10 equals negative 0.065 t. In order to solve for t, I'm going to divide both sides by negative 0.065. The negative 0.065s will divide out on the right-hand side, and we will be left with t equals negative natural log of 1/10 divided by 0.065. So it will take this many days in order for this element to be considered safe. So I'm going to go ahead and box in this answer. T equals negative natural log of 1/10 divided by 0.065 days, or t is approximately equal to 35.42 days. So I would say it would take 35 days for this element to be considered safe. Theorem. The decay rate K and the half-life T are related by the equation K times T equals the natural log of 2. If we solve this equation for T, we will get T equals the natural log of 2 divided by K. If we solve this equation for K, then we will get K equals the natural log of 2 divided by T. I have gone ahead and I've drawn clouds around these equations. Two, business application, present value. Example 2. New parents want to start an investment account for their child. They want to know how much they should invest now so that in 20 years the account will have $20,000. They are investing the money in an account that earns 4.5% interest compounded continuously. How much should they invest? So I'm going to go ahead and I'm going to highlight 20 years, and I'm going to highlight $20,000. And I'm going to highlight the 4.5% interest compounded continuously. I've highlighted all of these three things in yellow. Now I'm going to highlight in green the part that says how much should they invest. And I'm also going to underline in red the words compounded continuously. The value we are trying to find is called the present value. I'm going to draw a cloud around the words the present value. And the process of computing present value is called discounting. I'm going to underline that entire sentence. Solution. I'm going to go ahead and write down the equation A equals P times E raised to the RT power. This is our equation for interest compounded continuously. Inside parentheses to the right of this equation, I'm going to write in the equation P equals P sub 0 times E raised to the KT power. These equations are basically the same. They have the exact same setup. We just have some different variables here. I'm going to highlight the A in our first equation in green. I'm going to highlight the R in blue, and I'm going to highlight the T in yellow. I am going to go ahead and write down in place of A $20,000 because this is what we want to know. We want to know when will the account be equal to $20,000. So instead of A, I'm going to write 20,000, and we're going to have 20,000 equals P times E raised to the, instead of 4.5%, we're going to write down 0.045. We're going to convert the percent into a decimal. And instead of T, we're going to replace that with 20 for 20 years. So it'll be P times E raised to the 0.045 times 20 power on the right-hand side of this equation. I'm going to rewrite it so that we have P times E raised to the 0.045 times 20 on the left-hand side, and this is going to be equal to 20,000 and the 20,000 is now going to be written on the right-hand side. I'm going to divide both sides of my equation by e raised to the 0.045 times 20 power. On the left-hand side, the e raised to the 0.045 times 20 power, those two will cancel out, and I'll be left with p equals 20,000 times e raised to the negative 0.045 times 20 power. If we put this into the calculator, we will get an approximation. This is going to be approximately equal to $8,131.39 if we round to the nearest cent. I'm going to go ahead and box in that answer. So this is the amount of money that should be invested if we want $20,000 in 20 years. Theorem. The present value p sub 0 of an amount p due t years later at interest rate k compounded continuously is given by, I'm going to highlight the words present value p sub 0 in yellow. I'm going to highlight where it says amount p in green, and I'm going to highlight t years later in blue. I'm going to circle the words at interest rate k, and I'm going to underline the words compounded continuously. So the present value p sub 0 of an amount p due t years later at interest rate k compounded continuously is given by the equation p sub 0 equals p times e raised to the negative kt power. We're going to go ahead and box in this equation. Example 3. Frida wants to have $15,000 available in 6 years to pay for a kitchen remodel. The bank is offering a money market account earning 4% annual interest, compounded continuously. How much money should be invested now in order to have enough for the remodel? I'm going to highlight the $15,000 in green, because that's going to represent my amount P. I'm going to highlight the 6 years in blue, because that's going to represent the T years later. I'm going to circle the 4%, which is my interest rate K. I've underlined the words compounded continuously, and I've highlighted in yellow the words how much money should be invested now in order to have enough money for the remodel, and I have doubled underlined the word now. I've drawn an arrow pointing up from the word now up to the words present value P sub 0 in the theorem, because this is what we're looking for in this problem. We are looking for that present value P sub 0. I have underlined the words money should be invested now. The equation that we have here, the P sub 0 equals P times E raised to the negative KT power, will give us this answer immediately. But I'm going to go ahead and I'm going to use our equation from before, A equals P times E raised to the RT power, and show you how you can come up with the answer using this previous equation. Instead of A, we're going to substitute 15,000. That's going to represent our amount. And then we're going to replace the rate with 4%, but I'm going to rewrite it as a decimal as 0.04. And I'm going to replace T with 6. So we're going to have the equation 15,000 equals P times E raised to the 0.04 times 6 power. I'm going to rewrite it so that it says P times E raised to the 0.04 times 6 power is on the left-hand side. And we're going to write that this is equal to 15,000. I'm going to divide both sides by E raised to the 0.04 times 6 power. The E raised to the 0.04 times 6 power, these will cancel out on the left-hand side. And I'm going to draw an arrow for my equation pointing upwards and towards the right. So I'm going to write P equals 15,000 divided by E raised to the 0.04 times 6 power. So P is equal to 15,000 times e raised to the negative 0.04 times 6 power. Now if you compare this equation with the equation that I'm highlighting in yellow, which represents the present value P sub 0, you will notice that they have the exact same setup. I'm going to draw an arrow pointing down from my present value P sub 0 equation towards my answer that I just found right now. I'm going to highlight in yellow the P equals 15,000 times e raised to the negative 0.04 times 6 power, and I'm going to draw a red cloud around that. Underneath that, I'm going to go ahead and I'm going to give an approximation for this answer. P is going to be approximately equal to $11,799.42.
And we're going to box that answer in.